Chapter 17 is our first of 4 chapters talking about carbonyl reactions, and in particular it's talking about reactions of aldehydes, ketones, and nitriles. These 3 functional groups have in common that they all have a delta positive carbon that can be attacked by a nucleophile, and they do not have a good leaving group on them. Contrast that with the following 2 chapters, that would be 18 and 19, in which we have a carbonyl, delta positive, that's next to a potential leaving group, such as chloride. In this chapter we also look at the reactivity of carbonyls that are attached to a double bond or conjugated with a double bond, alpha and beta. And remember our nomenclature from last quarter that alpha is the carbon next to the carbonyl carbon. In this chapter we will focus primarily on reactions of very strong nucleophiles to aldehyde and ketone and nitrile carbons, delta positive carbons. And those very strong nucleophiles include our hydrides that are attached to either boron or aluminum, and our alkyl groups which are attached to metals, particularly Grignard reagents and alkyl lithium reagents. Interestingly, we are going to be working with Grignard reagents over several of the next 2 weeks of laboratory. We are also working with one hydride that looks like it ought to react the same as our sodium borohydride and our lithium aluminum hydride. That is, it's a metal with a hydrogen. However, this metal hydride has a alkali metal counterion, sodium, and it is highly ionic. It is really a small charged nucleophile. It does not have a counterion that could coordinate well with the oxygen, and it tends to act as a base instead of a nucleophile. And particularly, it will act as a base towards the hydrogen in the alpha position on our aldehydes and ketones, much like, and even on our nitriles, much like the way we saw in the previous chapter where we could make enolate ions that would act as nucleophiles. A typical reaction from this chapter would include taking a nucleophile, such as a Grignard reagent, which is nucleophilic on the carbon atom, reacting with the delta positive carbon on the carbonyl and kicking out a pair of electrons to give us a tetrahedral product, like so. The reaction typically happens in ether or THF solvent, and the magnesium ion helps stabilize the oxygen carbanion until protonation. One important thing to know is that we've gone from the equivalent of a very strong base, negative charge on carbon, the Grignard reagent, to a much, much weaker base, oxygen minus. Although sometimes we say oxygen minus is a strong base, if you look at the periodic table, it is significantly more electronegative than carbon, and it is about 20 to 30 orders of magnitude less basic than carbanion is. Therefore, the reaction is irreversible. The reaction goes forward only and waits around for us to protonate in a second synthetic step to give the alcohol product shown. Note that the new bond made during the Grignard reaction is the one that's in red. Likewise, we can add hydrides and make alcohols, or alkyls from organolithium compounds and make alcohols. But if we use sodium hydride, we end up removing an alpha hydrogen instead to make an enolate ion. The enolate ion can, of course, with sodium hydride react in an SN2 reaction, same as we saw in previous chapters. One reaction that we haven't seen before in the lecture book, although you did one in the laboratory, that is also included in this quarter is the Wittig reaction. And it also starts out with an aldehyde or a ketone, delta positive on carbon, as well as a nucleophile that is anionic on carbon. And that nucleophile is the Wittig salt. The Wittig salt is prepared through an SN2 reaction of a primary or secondary alkyl halide, like so. The triphenylphosphonium salt is then treated with a strong base like alkylithium to make the Wittig reagent, which is a dianion. The Wittig, removing the acidic hydrogen from the carbon next to the phosphorus will result in the formation of the Wittig reagent. The Wittig reagent then becomes a good nucleophile, adding to the carbonyl much the way the Grignard reagent did. After the initial addition, the phosphonium positive is attracted to the oxygen negative, and because phosphorus is a third row element, it can form extra bonds and does form a bond with the adjacent oxygen to make a unique intermediate known as a betaene, which can decompose by eliminating phosphine oxide to make an alkene. So the Wittig reagent allows us to make a CC double bond where there didn't used to be one before, in particular right down here in the middle. What used to be on the two ends of the CC double bond, one end was the aldehyde, and the other end was the carbon that gets transferred from the Wittig reagent.